Arran Fernandez is an associate professor at the Eastern Mediterranean University, Northern Cyprus. He was educated at the University of Cambridge, where he was the youngest student in 2010 and graduated as the top student senior wrangler in 2013. Following his PhD also at Cambridge in the Department of Applied Mathematics and Theoretical Physics, he has been working in Northern Cyprus. His research is on mathematical analysis of fractional calculus, emphasizing its connection with other fields of pure mathematics such as Clifford analysis, abstract algebra, analytical number theory, etc. He has published over 70 research papers and serves as an associate editor in three mathematical journals. It's nice having you, Aaron. You may please begin your talk.
Thank you, Pavan, for the introduction, and thank you to everyone who came here to listen to my talk today. So my topic is general kernels and parametrized families. So as this is a focus session related to generalized fractional operators, I want to talk specifically about how we can generalize the concept of a convolution kernel, or what sort of general functions we can consider as kernels. So I'm going to give an overview of various proposals that exist in the literature for general kernel functions, and then talk in detail about a proposal of my own, which comes from an algebraic viewpoint. And throughout this, we should bear in mind the concept of a semigroup property, because that's basically what we're looking for, because that was the research question that started this work. So here is the outline. I will do, as I said, this survey, introduce some algebraic concepts to be used later, and then the main new definitions are the real one-parameter families and real two-parameter families, followed by some further developments, conclusions, and references. So let me first talk about the phrase generalized fractional calculus, or general fractional calculus. Phrases like this we see in many papers in the literature, but there are many different meanings of this term. So the term generalized fractional calculus is used, for example, for fractional calculus with respect to functions, or fractional calculus with some general special function as a kernel, like Fox-Wright function, generalized hypergeometric function, for example, or for fractional calculus with some more general kernel in some function space, for example, Sonian kernels, analytic kernels, or there's other types of generalized fractional calculus, weighted, transmuted, so on. So some of these will be covered in the talk next week in the seminar series. But what I'm going to focus on is the general kernels. But the purpose of this slide is just to give my opinion that this phrase is too vague by itself without saying something more specific. What type of generalized fractional calculus do we mean? So if I'm talking about one of these types of generalized operators, I will not put in the title of a paper, for example, just general fractional calculus. I will say which type of generalization I'm thinking of. So let's now focus a little bit more. Many fractional integral operators have been defined using convolution kernels. So these are sometimes called the time-fractional operators because they are in one dimension. Whereas sometimes, other operators like the fractional Laplacian, for example, can operate in n dimensions. So these time fractional operators defined using convolution with some fixed kernel function. So the kernel function determines the operator, and then it can act on some appropriate function space. For example, the Riemann-Liouville and Caputo fractional derivatives are based on convolution with a power function, fractional power. Then we have Prabhakar fractional calculus with the modified three-parameter Mittag-Leffler function as a kernel. We have tempered fractional calculus, where the kernel is an exponential function multiplied by a power function. We have Fox-Wright functions as kernels, hypergeometric functions as kernels. There's many different types of kernel functions that can be used. So then, if you're looking at this topic as a pure mathematician, the question will naturally arise, what general kernel function can contain all of these as special cases? If you're a mathematician, you've never heard about this field before, and suddenly you hear that there's so many different types of fractional integral, fractional derivative using different kernels, but some of the behaviors are the same or similar, then you may think, okay, are these all special cases of some more general framework? Now, people have asked this question and people have attempted to answer by providing some general framework. So in fact, not only are there many different kernels, there are also many different proposals for general kernels that can contain all or many of these. So there's no single answer to what is the general kernel function. There's several types of general kernels have been defined. So here is a list of some of them. I put in bold a couple that have attracted more attention and people have worked more intensively with the Sonian kernels and the analytic kernels. But one can also find other proposals in the literature of the last 10, 15 years, which have not taken so much attention, but perhaps still worth mentioning as proposed general fractional integral operators. So I'm going to quickly overview these 5 proposals and specifically focus on some of their advantages and disadvantages. So let's talk about probably the most well-known of these, which is the Sonian kernels. Now, here is the general fractional integral with a Sonian kernel kappa. What does it mean to be a Sonian kernel? There should be a Sonian condition satisfied between kappa and some other function. The convolution of kappa and k is the constant unit function 1. That's a Sonian condition that gives a Sonian pair. And in fact, different function spaces have been proposed for general fractional calculus with Sonian kernels. So in the work of Kochubey from 2011, he used a list of assumptions that this kappa should satisfy for the specific applications he was looking at to evolution equations. But in the later work of Luchko, the assumptions were made weaker. So in Luchko's work, kappa is generally assumed to be just in the C alpha space, which I will show later in this talk. Basically, it's continuous on the open half line with possibly a singularity at 0, but an integrable singularity, just a power function, weakly singular kernel. So the big advantage of this proposal comes from the Sonian condition giving a natural inversion relation. You have a fractional integral defined with kappa, a fractional derivative defined with k, and they satisfy together a fundamental theorem of calculus, which gives a natural connection between the fractional integral and the fractional derivative, which is desirable. The disadvantage is when you look at this definition, you don't see any fractional parameter. So when you think about what is fractional calculus, it should be, we generalize the concept of integrating and differentiating from integer orders to non-integer orders. So there could be some parameter, alpha or nu, or whatever you want to call it, that plays the role of a fractional order. But here there is no parameter. So if you take subclasses of the class of Sonian kernels, you may fix. So in this C alpha space, it should be a fractional power multiplied by a continuous function. So you could fix the value of that fractional power, call that the order, and then you would get a subfamily. But when you look at Sonian kernels as a whole, there is not a fixed parameter, which means you cannot talk about semigroup property or continuity with respect to the order. You can talk about a semigroup property in the algebraic sense of having a semigroup. So if you have 2 Sonian kernels, kappa 1 and kappa 2, you put together the 2 operators, then you will get a new operator with Sonian kernel kappa 1 star kappa 2, the convolution. So you do have a semigroup property in that sense, but it's not a semigroup property with respect to a single real or complex parameter. So there are some advantages and disadvantages of this definition. Let me move to the second proposal, analytic kernels. So this was something that I came up with, published in 2019, but later we discovered that essentially the same idea had appeared in a paper of Reina in 2005. So the same idea, just from a different viewpoint, but basically the same thing with an analytic power series. So I think it's fair to cite Reina as well. So here the idea is we have 2 parameters, alpha and beta, which one could think of as like fractional orders. And we also have this function a, which is an analytic function. So in fact, a is not the kernel. We're not taking the convolution of f with a. We're taking the convolution of f with a modified by some fractional powers, which could turn out to be a singular kernel. But we still called it analytic kernels because the analyticity of A plays an important role. The big advantage of this definition is because A is analytic, it has a power series, therefore this operator can be expressed as an infinite sum of Riemann-Liouville integrals. And from that series formula, one can extend properties of Riemann-Liouville into properties of the new or the more general operators. The disadvantage comes when you try to define a fractional derivative, you try to look for a semigroup property or a fundamental theorem of calculus, because you can define a fractional derivative, you can get a fundamental theorem of calculus, but it's not very natural and it requires basically some assumptions on the function A. And if you want to get a semigroup property, that requires some even stronger assumptions, and it's not very easy to work with, let's say. You have to impose a bunch of assumptions in order to get nice properties like semigroup or even fundamental theorem of calculus. So again, advantages and disadvantages. Now, some of the lesser known proposals. Here's one from Agrawal from 2010. Here, this is very general in the sense that left-sided, right-sided, and two-sided operators are all covered by the same definition. We have an integral from 0 to t, another integral from t to infinity. But the problem is that, again, we cannot clearly describe the dependence on the parameter alpha. There is an alpha, which can be interpreted as a fractional order, but there is no conditions imposed on what sort of dependence on alpha we have. Therefore, we cannot say there is a semigroup property or a fundamental theorem of calculus or even continuity with respect to alpha without, again, putting a lot of extra conditions. Here is a proposal of Shileli, Karain, and Samet from 2019. They had both a kernel function k and a weight function omega, and there is an inversion relation. I've not included it on the slide because it's complicated, but basically there's a relation between k and omega which gives a fundamental theorem of calculus. So this is again the advantage. Similar to Sonin kernels, there is some kind of relation which allows a fundamental theorem. The disadvantage, similar to Sonin kernels, is that there is no fractional parameter. So we don't have any alpha here appearing where we can say there is a semigroup property with respect to alpha or continuity with respect to alpha. It's just a general integral operator. Finally, we have a proposal of Zhao and Luo, also from 2019. The advantage here is that they imposed conditions to restrict the limiting behavior, so alpha tends to 0 or 1. And they talked about applications in this paper. So I'm a pure mathematician. I cannot judge how really useful or relevant these applications are, but at least they try to motivate it from the applications viewpoint. The problem from the mathematical viewpoint is that this was not really mathematically formulated in a proper way. They never talked about what function space this k or this n should be in, what are the assumptions on these functions, especially this kernel function k. And without talking about that, you cannot get any semigroup property or fundamental theorem or any of these important relations. So that was an overview of 5 different proposals existing in the literature for general kernels. Unfortunately, even when you ask the question of what can we propose as a general kernel function, there is not one single answer. So I've made a more specific research question here. What is the most general kernel function such that we have a parameter, alpha, real or complex parameter that you can call the fractional order, and such that there is a semigroup property of the operators, of the fractional integral operators with respect to alpha? If we can answer this question, if we can construct this general family, then we can reconstruct much of the classical theory of fractional calculus. We can define fractional integrals, fractional derivatives, fundamental theorem of calculus, composition relations, etc. We can get a lot of things. So this is an interesting question to investigate. None of the existing general models really resolve this because either they don't have a fractional parameter alpha, or they do, but there is not a clear semigroup property in alpha, maybe except in some specific cases which reduce to Riemann-Liouville, so it's not the most general. So none of these existing proposals exactly answer this. And in fact, to answer this, we need a lot of theory from abstract algebra. Because if you think about what is a semigroup property, it's a concept that's used in analysis, but fundamentally a semigroup is something from algebra. So in the next slides, I'm going to look at Mikosinski's operational calculus, which is the main way that abstract algebra has kind of connected with fractional calculus, differential equations, and this sort of theory. And from there, we will get some algebraic terminology, which we can then use in constructing families of functions with semigroup properties and appropriate properties and relations. So Mikosinski's operational calculus, I summarize in the next two slides. Essentially, the idea is to apply algebraic structures and methods from algebra to interpret the operators of calculus. So in these slides, I'm using color coding. Anything that's blue is calculus or analysis. Anything that's red is algebra. And often we have the same thing interpreted in these two different ways. So the first step is to choose a function space. Function space is a concept from analysis, but essentially it's a set. We can put algebraic operations on this set and turn it into a ring, which is an algebraic thing. Then once we have the ring, if we can prove that this ring has no zero divisors, then it can be extended to its field of fractions. So this is an algebraic construction. I'll talk more about this later. The important thing to notice is in this bullet point, we only have red. We don't have any blue because the field of fractions is purely algebraic. The elements of this field, they exist in an algebraic sense, but they're not necessarily functions or operators. They cannot necessarily be interpreted in an analytic way, but they're still useful because integrals, okay, integration is an analytic thing, but we can interpret it as multiplication in the ring. Again, I will show this in detail in the next slides. If integration is multiplication, then what is differentiation? Differentiation is more or less an inverse of integration. Not exactly, but fundamental theorem of calculus. So then the inverse of multiplication should be division. And in a field, you can always divide because everything has an inverse in a field. So if integrals are ring elements, derivatives should be field elements. Now, if you have a differential equation, derivatives can be interpreted as multiplication or division in the field. So the differential equation becomes an algebraic equation. This algebraic equation you solve algebraically in the field. You find the solution. If the solution is in the ring, then the ring is also a function space, and therefore you get a strong solution. So here's perhaps a more visual way to show everything. Again, we have the blue and red color coding, but this time also left and right. So calculus stuff on the left, algebra stuff on the right. We start with a function space, turn it into a ring or a rung. So a rung is ring without I. It's a ring without a multiplicative identity. That we extend to a field of fractions, which has nothing corresponding on the left. It's a purely algebraic thing. Integration is multiplication in the rung, then differentiation is division in the field. And finally, sorry, there was supposed to be horizontal arrows here, but something's messed up with the LaTeX code. Anyway, it should go from a differential equation, starting on the left, over to the right, transform it to an algebraic equation, solve it algebraically to get an algebraic solution, then go back from right to left to get a functional solution. So in the fractional calculus setting of Mikosinski's operational calculus, the function space that's normally used is the C alpha space of Dymowski. First formalized in the 1960s by Dymowski and then used in operational calculus by Luchko and others in the 1990s onwards. C alpha space is defined as follows. It's the set of functions that are continuous function on the closed half line multiplied by a power function, t to the power p, where p is strictly bigger than alpha. What we normally consider is alpha equals -1, because then you have a space which is between the space of continuous functions and the space of locally integrable functions. So if your power is bigger than -1, then it's integrable at 0 and therefore on any compact interval. And because p equals 0 is also greater than -1, you include all continuous functions in the space c-1. Now, these function spaces are nested inside each other, and they satisfy this nice convolution relation, which means that for any alpha that's at least -1, the function space is closed under convolution, and then you can prove that it forms a rung. So a rung, again, is a commutative ring without multiplicative identity under the operations of addition and convolution. So this is our two operations in the rung. Addition is addition and multiplication is convolution. Now, from the rung, we can construct a field. So this is a general algebraic fact. Any ring or rung without zero divisors gives rise to a field of fractions. There is a theorem of Titchmarsh that gives that this particular rung has no zero divisors. So therefore, this construction works. Now, informally, the best way to think about this construction is that it's like going from the ring of integers to the field of rational numbers, or from any polynomial ring to a field of rational functions. Formally, the field is defined as a set of pairs quotiented by an equivalence relation. So you think of the pair as a fraction, f and g, like f over g, and the equivalence relation says that two fractions are equal if basically cross multiplication. And the operators in the field are exactly what you would expect, addition and multiplication of fractions. So this works, okay? This is proved in general that you have a field structure when you construct it like this. So we started with a function space, it's Dymowski space C alpha. That's a ring, we extend it to a field. In the field, we have multiplicative inverses. Remember that the concept of a multiplicative inverse is not pointwise division, because our multiplication is not pointwise multiplication. So f1 over g1 is not necessarily division like a polynomial over a polynomial is a rational function, because our division is the inverse of convolution. Of course, convolution is not normally invertible, but in this abstract algebraic setting that we have created, convolution is invertible because we have a field. It's interesting to note that the identity element in the field is a function, not a function, a field element, which has the property that when you take its convolution with any function, you get the same function. So I star f equals f, and that is a property that the Dirac delta has in distribution theory. So the identity element in the field sort of behaves like the Dirac delta as a generalized function. So there is somehow some overlap between this operational calculus theory and distribution theory. Now, integration, not fractional, just simple first order integration, is multiplication, which means convolution, in the ring by the constant unit function, which we denote as L. Because if L equals 1 everywhere, then L star G is simply the integral of G. Now, this theorem is the most important, the key part of the Mikusinski theory. This is how we go from integration to differentiation, from the ring to the field, and this is then used in interpreting and solving differential equations. So the field inverse, that's the inverse in the field m-1 of the element L. L is in the ring, therefore in the field. It has an inverse. We call that inverse S, and S acts as follows on differentiable functions. So S star f equals f dash, sorry, there should not be a brackets t there, I forgot to remove it, plus f of 0 times the identity element. This is very simple to prove. It's just a fundamental theorem of calculus. F of t we know is the integral of f dash of t plus the initial value. The integral of f dash is L star f dash by the thing at the top. Integration is convolution with L. So in the ring, we write this as f, left-hand side, equals L star f dash plus f of 0 L. This f of 0 term is a constant function, and any constant function is a constant multiple of L. Then this identity in the ring we multiply by S, which is the inverse of L. So S star f on the left-hand side. S and L cancel, so you get f dash on the right-hand side. S star L is the identity, so this is f of 0 I as the final term. So we get the stated identity. Notice that S is not a function, it's in the field. I is not a function, it's in the field, but f dash is a function as long as f is differentiable. So we have this relation. Some of the things involved in this relation may not be functions, but everything makes sense in the field, and this turns out to be useful in, for example, solving differential equations. So here's a brief history of Mikusinski's operational calculus. It was first applied by Mikusinski himself, Jan Mikusinski, the Polish mathematician, to ODEs. He published a book in 1959 describing this method. In 1969, a single paper was published by Gutterman from Gutterman's PhD thesis, applying this method to PDEs. This is a very underappreciated paper. It's had less than 20 citations since then, because Gutterman apparently left research after a PhD thesis and one paper. So Gutterman never continued, and nobody else picked up on this work either. Many other variants of Mikusinski's operational calculus have been surveyed. There's a nice survey paper originally in 1979 in Russian, translated to English in 1981, Brichkov, Brunnikov, Shishov. and it's been applied to fractional integral differential equations since the 1990s by Luchko with various collaborators, including Gorenflo, Hadid, Hilfer, and so on. So I've cited only one paper on this slide because there's not enough space for more. This is the 1999 paper by Luchko alone, published in FCAA. There will be more references at the end of the talk. Now, one important note is that the formulae you get coming out of the Mikosinski method look the same as the formulae you would get using Laplace transforms. So in that sense, the Mikosinski method is formally similar to the Laplace method, but it works in larger function spaces. So, for example, for Laplace transform, you need your functions to be exponentially bounded, some assumption that must be satisfied. But in Mikosinski, you only need this Stymovsky space, or even just the space of continuous functions in the non-fractional setting, which is, of course, much bigger. So functions like e to the power t squared can be considered in this space, even though they're not exponentially bounded and do not have Laplace transforms. So in that sense, Mikosinski's method is more powerful than the Laplace transform method. It's not become very popular, perhaps because of its reliance on theory of abstract algebra. In fractional calculus, however, this Mikosinski method has been used to solve differential equations that had never been solved before. So it has made some contribution to the field just by using this method. So Gorenflo and Luchko in the 1990s, they solved for the first time incommensurate multi-term fractional differential equations using this method. And they needed to create some new special functions, like multivariate Mittag-Leffler functions, to be able to do that, to be able to express the solutions. But this was something that had not been done before. So I've talked about how integrals and derivatives in the classical setting can be interpreted. What about in the fractional setting? Well, the fractional integral is also, of course, convolution with something, not with a unit function this time, but with a fractional power function. And here everything fits together perfectly, because if mu is positive, fractional integrals to positive order, and then this element is in c minus 1, because the exponent is strictly greater than minus 1 as long as mu is positive. So every fractional integral to real positive order can be interpreted as a multiplication, i.e. convolution, in the rung c minus 1. Semigroup property means that the set of these functions, h mu, literally forms a semigroup in the algebraic sense. It's a semigroup isomorphic to the semigroup of positive reals under addition inside the rung, which is the function space, c minus 1. Now, when you extend the rung to a field, everything has inverses, so the semigroup becomes a group. Okay, this is a multiplicative semigroup. It's under convolution, which is multiplication in the rung. So now we get a multiplicative group. The elements of this group are the h mu functions, their inverses that we call s mu, which are not functions, and the identity element in the field. So these together form a group. The semigroup of positive reals has become the group of all real numbers. So this group is isomorphic to the group of real numbers under addition. Here are the theorems on interpreting fractional derivatives using this operational calculus. So S mu, you remember, is the inverse of H mu. H mu is the interpretation of the fractional integral, and both fractional derivatives, Riemann-Liouville and Caputo, can be interpreted as convolution with S mu minus something extra, which is basically depending on initial values. Fractional initial values for Riemann-Liouville, ordinary initial values for Caputo, as one would expect. I want to briefly mention another type of fractional calculus, because I will come back to this as an example later. Rabakov fractional calculus is nice because it has a lot of the same properties as Riemann-Liouville and Caputo, but in a more general setting, still managing to preserve things like semigroup property, analytic continuation, and so on. So here's the definition. We have the Rabakov fractional integral, convolution with a modified three-parameter Mittag-Leffler function, and then the Rabakov fractional derivatives are defined by combining a fractional integral with an ordinary derivative, as usual. So it can be shown using series formulae that these operate between the same function spaces as the classical Riemann-Liouville and Caputo operators. So the Rabakov integral sends, for example, c minus 1 into itself. It is again a convolution operator. So the Rabakov integral is convolution with this element, this function that we've used as a kernel, we call that P. And I've written it as P beta gamma, suppressing the dependence on alpha and delta because the Prabacher semigroup property is a semigroup property in only 2 of the 4 parameters. So you have 4 parameters, but the semigroup property is only in beta and gamma. Alpha and delta can be fixed, can take any fixed values. Alpha is positive, delta can be anything. And then these functions P form a multiplicative semigroup as beta and gamma vary. So beta, again, must be positive, and gamma can be anything. We have a semigroup which is isomorphic to the half plane, R plus times R, beta positive, gamma anything. And, of course, the semigroup, when you go into the field, extends to a group again. So what's the group you get? If a semigroup is the half plane, the group is going to be the whole plane. So again, we have this semigroup property structure. We can interpret it algebraically, just it's in 2 dimensions instead of 1 dimension. So you may already guess by now, looking at the headers in this talk, of where this is going. So we're going to think about semigroup properties with 1 parameter or with 2 parameters, and then develop a general theory. So I list here a few more algebraic facts, which are perhaps obvious from the algebraic viewpoint, but worth noting and remembering from the analytic viewpoint. First one is that if you have any subset of the ring, this is C-1 cross means the ring without 0, then it generates a subgroup in the field. Now that's a multiplicative subgroup because every subset generates a subgroup. It's just a basic algebraic fact. If you have an element of the subset, then its inverse and all powers must be in the subgroup. Okay, now next lemma says that if we have, again, a subset, but we require that it contains the element 1, or L, as we've called it, the constant unit function, then for any g in this subset, which is also a C1 function, its derivative, modified by an initial condition, must be in the subgroup. So in a sense, this is sort of closed under differentiation. Not exactly, because you have this modification with the initial condition, but you can think of it like that. And the final lemma is just sort of interpreting these algebraic facts in a little more analytic way. So if you have any integral operator which is given by convolution with an element of C-1, so let's say convolution with some function g, then the set containing just g, the singleton set, we can say that's a subset X. It generates a subgroup, and this subgroup intersected with C-1 is going to be a semigroup of functions that give operators. So if you start with one integral operator, it can be embedded into a family that has a semigroup property. And this is important to mention because there has been some debate in the fractional calculus community about whether certain operators satisfy a semigroup property or not. But this shows that everything satisfies a semigroup property if you put it into a big enough family. So if you find some operators that don't have a semigroup property, then that just means that you're looking too narrowly and you need to perhaps add another parameter or somehow see this family you have as a subset of some bigger family of operators which does have a semigroup property. So these are just basic algebraic facts. Now we've got our algebraic background, we've got our research question about general kernels, so it's time to begin on the really new work. Okay, so let H be a subsemigroup of C-1. So this is a multiplicative semigroup. And we're going to assume that H is isomorphic to the semigroup of positive reals under addition. Then this is a set of functions. So we can write the elements of H as just G alpha. Using this isomorphism, we say G labeled by alpha, where alpha is a positive real. And because of the isomorphism, we have a semigroup property between these functions. A semigroup generates a group in the field. So if we go for M-1, then we get a multiplicative subgroup. What are the elements of this subgroup? We have the functions in H, their inverses in the field, and the identity element. That's it. It's like positive reals, negative reals, and 0 in the middle. So that's isomorphic to the group of real numbers under addition. Now, the next theorem is somehow trying to describe the power function associated to each G alpha. If you remember the definition of this C-1 space, So C-1 every function in there has an associated power p, which is greater than -1. But p is not uniquely determined by f, because if you have, for example, t to the power 0.5 times f1 of t, then that is also t to the power 0.4 times a different f1, which is also continuous because it's t to the power 0.1 times the original f1. So for every given p, any smaller p will also do. Therefore, therefore we define this m to be the sup of all possible p. There is not a unique p, but there is a unique supremum, and that's how we define the power associated with a given function in C-1. Now, I've managed to prove a bunch of properties of this m function, including that it's positive, it's increasing, the limiting behavior at the two ends, and some kind of convexity condition. I did not manage to prove that this function must be continuous. I tried to prove that. It felt like it should be true. I didn't manage to find a proof. But the limiting behavior together with the increasing condition are enough to show that G alpha, the function, is always continuous for all sufficiently large alpha. So when you get beyond a certain point in the semigroup, all of these functions are continuous. Now, we can define operators because we've got functions in C-1. You can take convolution with these functions. Then you have I alpha, it's convolution with G alpha. These operators have a semigroup property as imposed by the semigroup structure. But can we really call these fractional integrals? Because arguably what we have so far is just an arbitrary convolution operator, convolution with some function. There is a semigroup property, but is there really a fractional integration structure? Where is the connection with fractional calculus or even with classical calculus? So the way to make that connection is to make sure that classical calculus is included as the integer order case. So if the classical first order integral is part of this family of operators, then it is a generalization of classical calculus, and we can think of it as fractional calculus. Now, without loss of generality, we want to assume that the element 1, or L, this constant unit function, is in H. And because the semigroup has a scaling automorphism, we can assume that the value of alpha corresponding to this element is alpha equals 1. So that means the integral to order 1 is exactly integral to order 1. So here's the main definition. A real one-parameter family is given by, there are three conditions. You need a semigroup structure, so it should be a sub-semigroup of C-1 under multiplication. As a semigroup, it should be isomorphic to the semigroup of positive reals under addition, and it should contain the element 1, the constant unit function. If you have those three conditions, then I call this a real one-parameter family. Then we write H as a set of these functions G alpha, G1 equals 1, and we define a fractional integral operator for every positive real number alpha defined by convolution with G alpha. So now we've got this family, let's look at some properties. If alpha equals 1, we have a classical first order integral. That makes sense, that's part of the assumptions. There is a semigroup property, that's also part of the assumptions. Now here's something less obvious. For every alpha, the derivative of G alpha, well, G alpha is a C1 function and its derivative is G alpha minus 1, whenever alpha is greater than 1. If alpha is greater than n, then G alpha is a Cn function, and again, its derivative is alpha minus 1. So differentiating is subtracting, reducing alpha by 1. What about limiting behavior? As t tends to 0, what happens to G alpha of t? If alpha is greater than 1, it goes to 0. If alpha is less than 1, it goes to infinity, it blows up. This is pretty much like power functions, but we're not just dealing with power functions here. This could be a more general family of functions. Next theorem, from this going to 0 or blowing up behavior, we can say the corresponding integral operator is singular if alpha is less than 1, non-singular if alpha is greater than or equal to 1, just like Riemann-Liouville integrals. If alpha is less than 1, then G alpha convolution G1 minus alpha is G1, which is 1 constant unit function, and that's a Sonian condition. So if alpha is less than 1, they are all Sonian kernels. For bigger values of alpha, they are generalized Sonian kernels in the sense of Luchko, who defined Sonian kernels to arbitrary orders by extending the Sonian condition. So somehow this theory that I'm creating fits within the theory of Sonian kernels. It's a sub-theory. It's a special case of Sonian kernels. But being a special case doesn't make it worthless, because we have special properties coming out of the fact that here we have an explicit fractional order parameter, which the very general theory of Sonian kernels does not necessarily include. So now we define fractional derivatives. We have G alpha for all positive values of alpha. G0 we're going to define to be the identity. Remember, this is a field element, but not a function. And that lets us define Riemann-Liouville and Caputo type fractional derivatives by combining the fractional integrals we have with the ordinary derivatives. Here we've got G n minus alpha convolution and the operation of differentiating n times. What is n? N can be the floor of alpha plus 1 for alpha non-integer, or n equals alpha for alpha integer. This is the same as saying n is the ceiling of alpha, but there's a reason why I've written it like this, which you'll see a bit later. Consider the case n equals alpha. Then we have derivative to the order n, and then it's a nth derivative of what's g n minus alpha. G n minus alpha now is G0, which is the identity. So identity convolution f is just f. And both of these become the nth derivative, the classical nth derivative, if alpha equals n. So in that sense, they are truly fractional derivatives. They include classical derivatives as a particular case. And that's why we needed an idea of what G0 should mean. But it makes sense to mean the identity, and then the integration to order 0 would be the identity operator. Function spaces for the fractional derivatives. For Riemann-Liouville type, we have this omega space. For Caputo type, we just require m times differentiability. And then we have these nice mappings from the spaces with differentiability conditions into C-1. A few more nice facts here. The Riemann-Liouville derivative we have defined using this particular n, but we could instead take n to be any bigger natural number. N could be anything that is a natural number such that n minus alpha is still positive. So here we've said capital N, which is perhaps more general than the lowercase n, could be anything satisfying these two conditions, but the operator is the same. The fractional derivative is the same. If f is C1, then it must be in the omega space for all alpha up to 1. And if f is the fractional integral of some g, then f is in the omega space and the fractional derivative of f equals g. So this last property is a sort of inversion relation. The derivative of the integral comes back to the original function, and we generalize this to a fundamental theorem of calculus. So we have these nice natural relations, the fractional derivative of integral, integral of derivative for both Riemann-Liouville and Caputo type operators. Now, that gives rise to an algebraic interpretation, because if you remember from the classical Mikusinski theory, what we need to get the algebraic interpretation of the derivative is simply the second fundamental theorem of calculus. The integral of the derivative is the function minus the initial condition. So what we're going to see over here is we have a second fundamental theorem of calculus, and from that we can get the algebraic interpretation of the fractional derivatives in both cases. So here's the Riemann-Liouville and Caputo fractional derivatives, G alpha inverse, that's the algebraic inverse, star f minus something involving initial conditions. So everything after the first term is involving some sort of initial values of f, fractional initial values for Riemann-Liouville, ordinary initial values for Caputo. If alpha is between 0 and 1, then we have these simpler expressions with just a single initial value term after the G alpha inverse term. Now, we've constructed a general theory. What kind of examples can we find? Obviously, the archetypal example is the original Riemann-Liouville fractional calculus, where the G alpha functions are fractional power functions. So in this case, all the results done above reduce to well-known results about Riemann-Liouville and Caputo operators. Is this the only real one-parameter family? Now, this is an interesting question. I've not actually managed to construct another example, but this question I think will be interesting to answer no matter what the answer is. Because if the answer is yes, then one could say, okay, this theory is trivial, it's just Riemann-Liouville, but we've proved then a universality property of Riemann-Liouville. It's the only family of operators satisfying some natural set of conditions. If the answer is no, that's again interesting because we have then some other families of operators with the same nice properties like Riemann-Liouville to construct a fractional calculus, but they're not Riemann-Liouville. So there's a short paper of Cartwright and McMullen from the 1970s, which proves a sort of universality condition of Riemann-Liouville under some other assumptions, and maybe some ideas from there can be used to prove a universality condition here. But what happens if the answer is yes, if we prove this is the only real one-parameter family? Does that mean all this work is wasted? Well, no, because there's a question we've still not considered. What about Riemann-Liouville with complex orders? Everything we've done so far here has assumed that alpha is a positive real number, or a real number in general. And that was really an inherent part of the construction, because when we defined these real one-parameter families, we took a subsemigroup isomorphic to the semigroup of positive reals under addition. So when we consider complex order Riemann-Liouville, we really need a different construction. So here comes the next section. We now let H be a semigroup isomorphic to the half plane. So R plus times R. So that's all real numbers in one direction and just the positive real numbers in the other direction. That's a half plane. And the elements of this H, it's a sub-semigroup of C minus 1, which is a function space. So again, the elements are functions. We call them G, alpha, gamma, where alpha is positive and gamma can be anything. And we have a semigroup property, and this semigroup generates a group. Now, the group elements are not so simple as before. We have the semigroup elements, the H, functions in H, and we have their inverses, and we have the identity, but that's not all. We have a whole kind of line of functions. Think of it as we've got the open half plane, then their inverses will be the other open half plane. In between them, we still have a line to fill in. So these elements I've called G blank gamma, which are in the field m-1. This is a multiplicative group, subgroup of m-1 cross, which is isomorphic to the plane, just R times R, the real plane under addition. M, we define again to be the power associated with each of these G functions, the soup of all the P and so on, the same definition as before, and we can prove pretty much the same properties as before. So this M function is strictly positive, strictly increasing with respect to the first parameter only, limiting conditions with respect to the first parameter and this sort of convexity condition. And these things are enough to show that for sufficiently large alpha and for all gamma, these functions are continuous on the closed half line. Now we define a real two-parameter family, which is given by, again, three conditions, just slightly different this time. We have a subsemigroup, so there must be this semigroup structure, isomorphic to the half plane, not the half line, and containing the constant unit function 1. So those are the three conditions. If we have those, we have a real two-parameter family. Again, without loss of generality, we can assume that our unit function 1 is at alpha equals 1 and gamma equals 0, because there is a scaling and shifting automorphism of the half plane. The fractional integral of order alpha and gamma in this family is defined as the convolution with the function g alpha gamma. So similar properties to before. First order integral is included. We have a semigroup property. Differentiation corresponds to reducing the first parameter alpha by 1. And limiting behavior as t tends to 0, the function goes to 0 if alpha is greater than 1 or to infinity if alpha is less than 1. That means the corresponding fractional integral operator is singular if alpha is less than 1, non-singular if alpha is greater than or equal to 1. If alpha is less than 1, we have Sonian kernels, because g alpha gamma star g 1 minus alpha minus gamma is going to be the unit function. Sonian condition is satisfied. If alpha is bigger than 1, then it's still a generalized Sonian kernel in the sense defined by Luchko with arbitrary orders. So again, the theory fits within the existing theory of Sonian kernels, but now we have two real parameters instead of one real parameter. Here's the fractional derivatives. Now, the interesting thing here is we must define n to be the floor of alpha plus 1. Even if alpha is a natural number, we cannot use n equals alpha. So let's say alpha equals k, that's a natural number, we must still take n to be k plus 1 and not k. Because if n equals k, if n equals alpha, then we're looking at operators I, 0 minus gamma. And what is I, 0 minus gamma? We have not defined that. We have defined fractional integrals where alpha is positive, and we can say that the fractional integral to orders 1, 0 would be the identity operator. 0, 0, would be the identity operator. But if it's 0, something else, integral to order 0, minus 27, then what is that? In the one parameter case, we could take n equals alpha because the one parameter I0 is just the identity, but now we have I0, minus gamma, which is not defined, so we must take n to be always strictly bigger than alpha. This is a subtle difference, but an important difference between the one parameter case and the two parameter case. Let me remark more about this edge case. What are the elements G blank gamma? So remember, in the group, we have semigroup elements, their inverses, and these G blank gamma. Why did I call it blank, first of all? Why not G 0 gamma? Well, I don't want to confuse the notation because G subscript alpha gamma is a notation for functions, and alpha must be strictly positive. If alpha equals 0, it's not a function anymore. It doesn't make sense to call them G 0 gamma. It would get confusing. They're also not inverses of elements in H. So they're not G something inverse either. The only thing I can call them is G blank gamma. There is no first parameter. They're special edge cases. They're not in H. They're not in H inverse, but they're in the complete group. If we consider operators with alpha equals 0, as I said on the previous slide, we cannot do fractional integrals with alpha equals 0, only fractional derivatives with alpha equals 0. So when alpha equals 0, we've got fractional derivatives. They look like this. And these formulae do not technically involve the G blank gamma elements. So you might think the derivative to order 0 gamma would be f star G blank gamma, but remember G blank gamma is not a function. So when we have an algebraic interpretation, when we have a field structure as see below, then we can get something involving G blank gamma, but not just as functions because they're not functions. Function spaces for the fractional derivatives, similar to before, we have an omega space for the Riemann-Liouville type derivatives, and then simply requiring differentiability for the Caputo type derivatives. Again, as before, the Riemann-Liouville type derivative can be defined using any capital N that's a natural number and strictly bigger than alpha, not only the fixed lowercase n that we defined as the floor of alpha plus 1, it could be anything bigger than that. If we have a C1 function, then it's in the omega space for all alpha up to 1. If we have f being a fractional integral of g, then f is in the omega space and its fractional derivative is g. That's an inversion relation which gives a fundamental theorem of calculus. So here's the fundamental theorem of calculus for Riemann-Liouville. It's a bit more complicated this time. We need to split it into two cases, for alpha not an integer and alpha an integer. And for Caputo, again, we split into two cases, alpha not an integer and alpha being an integer. Now, from these results on the second fundamental theorem of calculus, as before, we get algebraic interpretations in the Mikosinski field. So for the Riemann-Liouville type derivative, in the field is interpreted as G alpha gamma inverse star f minus a bunch of initial value terms. That's if alpha is positive. If alpha is negative, it looks like this. So here, notice we have the 0, alpha equals 0, so D 0 gamma, and we use these G blank gamma elements, or blank minus gamma in this case. And the other thing is just an identity. So not a function, but, useful in the construction. For the Caputo fractional derivative, we have to split into three cases. Alpha is not an integer, alpha is a positive integer, and alpha equals 0. And again, if alpha equals 0, we've got G blank minus gamma star f. So those blank elements actually come into play. Whereas in the other constructions for alpha positive, then every time we see a G, it's not with a blank. It's either G as a function or G inverse, so the multiplicative inverse of a function, but not the blank elements. Now, what about examples of the general theory? Again, of course, the archetypal example is Riemann-Liouville, this time with complex orders. Alpha is the real part, gamma is the imaginary part. So, as you know, when we define Riemann-Liouville fractional integrals, we require the real part of the order to be greater than 0. So the real part is strictly positive, the imaginary part can be any real number. And then again, all of the results above reduce to well-known theory of Riemann-Liouville fractional calculus. The edge case, where you have this G blank gamma, that would be the derivatives of imaginary order, which are a special case requiring special attention. Papers have been written just about derivatives of imaginary order, that particular case. Here is another example. This is very important because we see that we have two different types of examples with different types of structures. It's not a trivial theory. It's not reducing to one example, because complex order Riemann-Liouville is one case of this theory. Real order Prabhakar is another case. For any value of mu and any value of delta, these functions will give a real two-parameter family. Alpha is strictly positive and gamma can be any real number. So it's exactly as in the requirements, and you can check that the semigroup property is satisfied and these things form a semigroup. This is already known from the theory of Prabhakar fractional calculus. Here, the edge case is actually the non-singular case. So G blank gamma reduces to non-singular Prabhakar fractional calculus, which is a particular case. I'm not going to go into talking about non-singular kernels here, but let's just say that they've had a lot of attention in the literature. Now, here's another special thing we can do. I'm coming to the end now. I'm just wrapping up with some concluding remarks. So as a group, not thinking about analytic structure, but just algebraic structure, the complex plane is isomorphic to the real plane. So if we have some family of functions or family of operators parameterized by one complex parameter, then we can also consider that as parameterized by two real parameters. Now, there is a very special case of where you have parametrizing by two real parameters, alpha and gamma. Think of it as one complex parameter, alpha plus I gamma, and require analyticity with respect to that complex variable. Then we get the Riemann-Liouville derivative as the analytic continuation of the fractional integral. Of course, this is not stated precisely. So to define and state this properly, we need to talk about fixing a function and fixing a value, and then it is an analytic function of alpha plus I gamma. So we're not talking about operators depending analytically on parameters, but essentially this is the idea. And when you make it rigorous, when you fix the function and the t, then everything comes out in exactly the same way as for complex order Riemann-Liouville. So we have this analytic continuation property for Riemann-Liouville fractional calculus. The same idea extends to this general setting. Mikusinski's operational calculus is an algebraic method. We've done an algebraic construction here. So it makes sense that these things would be sort of consistent with each other. So the new general operators can be used to formulate differential equations and solved using Mikusinski's operational calculus. Of course, the results thus obtained are more general than classical results with Riemann-Liouville, Prabhakar, and so on. Those operators, they're all special cases of the new structure. And of course, there's the natural question of how to extend this further. If you've got a theory with one parameter and you've got a theory with two parameters, then why not go to 3 or 4 or n parameters? So this is my next step in developing this work, is going to real n parameter families, considering the associated semigroups of functions and groups of operators, and what types of fractional calculus one can reach as special cases. For example, so far we've got real order Riemann-Liouville, complex order Riemann-Liouville, but only real order Prabhakar. So complex order Prabhakar one can also think about. And then there's the operators using multi-parameter Mehta kernels, which came out from solving multi-term fractional differential equations. And if we make the theory general enough, we can include all of these as special cases in an abstract algebraic setting. So this was the research question that we started with. I've created a theory to answer this question using ideas from abstract algebra. So the theory was firstly for functions and operators depending on one real parameter, and then it was extended to two parameters, which enabled a general structure to include both Riemann-Liouville and Prabhakar. So definitely not a trivial structure, not just one possibility in there. And standard facts of fractional calculus, like a semigroup property, a fundamental theorem, and so on, still hold within this general structure. So the moral is that combining fractional calculus and abstract algebra can be a very powerful thing to do. The remaining slides are references. So I think these ones you've already seen on my earlier slides. These are all references related to general kernels. And then these ones are all related to Mikusinski's operational calculus. So some of them you've seen, but the later ones on this slide I didn't include earlier because there wasn't space. And finally, some other interesting papers. The first one here is a recent paper of mine doing Mikosinski for fractional PDEs for the first time. Then we have Luchko's work on Sunnian kernels for arbitrary order, the Cartwright-McMullen paper that I mentioned, a sort of universality property of Riemann-Duval. And the final one in red is the paper that this talk is based on. So if you're interested in this and you want to see more detail and proofs of all the results and everything, you can find this. It was published earlier this year in Complex Analysis and Operator Theory. So that's the end. Thank you for your attention.
Thanks, Arran, for the interesting talk. For questions, I kindly request to raise your hands, and I'll call out your name as they appear on my screen. I already see Professor Scalas has a raised hands. Please go ahead, Professor Scalas.
Thank you very much. Can you hear me?
Yes.
Very good, very well. So thank you very much for your very interesting talk. And I would like to come back to your first question about possible uniqueness of one parameter operators. Essentially, yeah, that one, yes.
Yeah.
The recent paper, maybe it is not unique. There is a recent paper by Becker-Kern, let me see, and Svenja Lage, whose title is On Self-Similar Bernstein Functions and Corresponding Generalized Fractional Derivatives. And it seems it boils down to what physicists would call scaling properties, but they are self-similar properties of the processes that are related to these operators. And yeah, this is just a comment. Let's see if I can. Yes, so you find the paper link in the chat.
Oh, thank you very much. Yes, I was going to ask about the link.
So maybe if you can find a partial answer to this question there. It is possible. Unfortunately, I'm not yet very familiar with your theory to see an immediate, let's say, to see immediately that there is a relation, but there might be, essentially. So I came into this problem of uniqueness from a different story coming from probability somehow. Maybe it's less interesting for the audience today, but just wanted to highlight that there could be a potential answer here. I also would like to apologize that I cannot show my face because the camera is not working now. So thank you very much again.
Thank you very much for the comment. I will check this paper.
Does anybody else has a question? If you have a question, you can unmute your mic and go for it.
Can I ask a question, please?
Yes, Prashant.
Yeah. You see, thank you, first of all, for very interesting talk, Arran. You have shown very advantages of this theory. For example, we can define complex order derivatives. But is there any equation, fractional differential equation, which we cannot solve by using the Laplace transform, but we can solve it by using this semigroup theory?
Well, the thing that can be compared with the Laplace method is perhaps the Mikosinski method. So the Laplace transform method can solve many of the same types of equations, but Mikosinski's method, the operational calculus, which is the algebraic method, can solve the same equations and more because, for example, if you have an inhomogeneous term that is e to the power t squared that has no Laplace transform because it's not exponentially bounded, but you can still use Mikosinski's method to solve differential equations involving functions like that. So the expressions will look the same, but rigorously, one cannot use the Laplace transform with those functions, but you can use the Mikosinski method.
Thank you.
Does anybody else has a question? You can unmute your mic if you have a question and go for it. Right, I don't see any raised hand or anybody else having a question. So it seems to be a good point to stop here. Thanks, Arran, again for the very interesting talk and engaging everybody else on this
Thank
Friday
you.
afternoon. Thank you very much. Bye-bye.
Thank you. Bye-bye. Thanks everyone for attending.